Now let us see the chemical reactions of amines. The first to be discussed is their basic nature of amines. See, amines are, due to the presence of that lone pair on the nitrogen, are very good Lewis bases. This can clearly be seen when we react them with any of the halogen acids. They forms the corresponding ammonium halide salt. So this salt is formed. We can react them with any of the other mineral acid also, like we can react them with nitric acid. Again they form ammonium nitrate salt. The formation of these salts shows that these are very good Lewis bases. The most interesting thing about these amines is this, that they even in the aqueous medium are very good bases. These amines in water accepts H plus and gets converted into NH3 plus and releases OH minus. We can write down their equilibrium constant as RNH3 plus OH minus RNH2 and water. Water being the solvent, its concentration doesn't increase, so if it remains constant. So if we bring this constant along with this, like this, it's called Kb, dissociation constant of the basis amine, and it is written as RNH3 plus OH minus RNH2. So this is the expression of the Kb, which is going to tell us how stronger a particular amine is. Or we can have pKb, which is minus log of Kb, which is inverse value of the Kb. So this is how we can assess by the value of the Kb that which amine, whether primary, secondary or tertiary, is more basic or less basic than the other one in comparisons. Now, before moving to any other reaction, let us compare the basic nature of the different amines and ammonia. It's between different amines and ammonia. See, what you need to know in this case is, like, this is your primary amines, this is your secondary amines, and this is your tertiary amines. Now the basic nature depends on the first factor is plus I effect of R group. And remember, basic nature is inversely proportional to plus I effect. More is the plus I effect, lesser is the, it will come up directly. More is the plus I effect, more is the basic nature. So in this way, primary amine is having plus I effect from only one side. It is having plus I effect from two sides, and tertiary amine are having plus I from three sides. So therefore, the order is, it will be tertiary, secondary, primary. And if we include the ammonia, ammonia will be at the end. This is decreasing order, remember the order. Ammonia, why ammonia in the least? Because it's not having any R group to show plus I effect. So this is the order which we again also follows in the gaseous state. Because in gaseous state, no other factor plays important role than the plus I effect of the R groups. The second factor is steric factor. And basic nature is inversely proportional to steric hindrance. More is the steric hindrance, less is the basic nature, because less attack of the on the nitrogen takes place. Therefore, the most maximum steric hindrance is in tertiary, then in secondary, and it is least in primary because of the only one R group. That is why, therefore, on this basis, we can conclude that the decreasing order of this will be primary, then secondary, then tertiary. And if we include ammonia, ammonia will be maximum in this case. So that's the two factors we have. The third is, let me rub out this one. The third factor is solvation of conjugate acid, or the stability of conjugate acid which is formed when they combine with water. We know the moment they combine with water, they acquire one more H and a plus charge. One more H and a plus charge. One H and a plus charge. Now the primary one is having 3H, so it will be solvated to the maximum extent because it will be able to form hydrogen bonding with 3 water molecules. Followed by your secondary, because it will be able to form hydrogen bonding only from these 2 hydrogens, and the least will be your tertiary because it will be able to form hydrogen bonding only from the 1 H it is acquired in the form of a conjugate acid. So what we find is that the decreasing order is primary, secondary, and tertiary. Now, this is what are the 3 factors we have. Now, what you need to know is the steric factor plays important role only when the R is, this is relevant when R is methyl, else it is irrelevant. So now, therefore, let me rub out this one. Now we don't need this. Now we have to write down the overall trend is that if R group is methyl, then the trend is in the decreasing order. See, the most important then are, usually the most important factors are this plus 1 and the plus 3, first one and third one. First one makes tertiary most basic. The third one makes primary most basics. Both they count as the effect of each other, so the most basic is your secondary. Then, since R is methyl, steric factor plays an important role. So after secondary amine, since we have R group methyl, the steric hindrance is least for primary, as well as it gets maximum solvated. So most basic is after secondary is your primary, followed by tertiary, and then we have ammonia. Whereas if R group is ethyl or a bigger group, then the decreasing order what we find is, remember, then the steric factor is of no importance, because the steric hindrance of either the ethyl when it is primary or secondary or tertiary is almost equivalent. So what we have is mainly the first and the third factor contributing towards the basic nature. Again, since this makes tertiary to be most basic, this makes primary to be most basic. The one which dominates is the secondary. Then the plus I effect dominates. That makes tertiary, because since the R groups are now very bigger one, their plus I effect is very strong. So that makes tertiary to be most basic, the second one number, and then the primary, and then the ammonia. So this is the basic nature of the amines we have. Remember, for alkyl amines, we have this overall basic nature's trend. Now let us compare the basic nature of aromatic amine and aliphatic amine. If we see the aromatic amines, we can clearly assess from there basic nature of aromatic and aliphatic amines. See, we draw a very simple conclusion that, aromatic amines are less basic than a normal alkyl amine. Why they are less basic? The reason is they show what? Plus R effect. Due to this plus R, the nitrogen acquires plus charge and its lone pair gets dispersed on the benzene ring. As a result, what we find is the orthopara positions, this will shift here, orthopara positions acquires negative charge. The resonating structures are like this. So that is why this is orthopara directing for electrophilic substitution reactions, and due to this plus R, this aromatic amines are less basic than the normal alkyl amines. Also remember, in case of aromatic amines, electron withdrawing groups decreases basic nature by their minus R or minus I effect, whereas electron releasing groups increases basic nature by plus R or plus I effect. So what we find is, if we have to compare the basic nature of like these three amines, let it be A, B and C, what we find is the least basic is NO2, para-nitroaniline. The reason being because of its minus R effect, so it is B. Then we have normal aniline because it's not having any releasing group, whereas methoxy, because of their plus R effect, is the most basic. So this is how we have the different trends of the basicity of the different type of substituted aromatic amines. The second reaction of amines is their alkylation. Now any amine can be reacted with alkyl halide. We know this. This is almost the Hofmann's exhaustive ammonolysis. These being, this is primary amine, these being very good nucleophiles, attack on this and forms what? Rx, R2NH plus HX. So secondary amines are formed, and this reaction can move on further and it can give us tertiary and quaternary ammonium compounds. We know about this reaction. Similarly, the third reaction is their acylation. It means reaction with this acyl group. Now any amine can be reacted with this acyl group. In basic medium, the H here and the Cl goes out, and what we get is this amide being formed plus HCl. Let us see now the examples. This is called acylation. Let us see, we have ethanamine, reacted with acetyl chloride. Therefore, we call this as acetylation, because now we are knowing that which acyl group we are introducing. Now what happens is, this being nucleophile, its attack takes place here. So double bond shifts here. We get CH3, CH2, NH2. It requires plus charge, C, CH3. Let me put it like this, O negative, CH3, Cl. Now what happens is, this withdraws the electron from here, it becomes what? Your NH. And similarly the Cl goes out, this gives electron back here. So what we get is CH3, CH2, NH, C double bond O, CH3 plus H plus and Cl minus. So this is how we get the amide. And now this will be called N-ethyl acetamide or ethanamide. Sorry, ethanamide. So its name will be, remember, it will be N, let me write down here, it will be N-ethyl ethanamide. So it will be an amide. That's most important to note. Now remember, the same thing can be done for aromatic amines also. So if we react them with this acetyl chloride in basic medium, what we get is this compound. This is called N-phenyl acetamide. Now similarly, remember, we can react them with this benzoyl chloride. In basic medium, then this reaction will be called benzoylation, and the product obtained will be NH, C double bond O, and it will be called N-ethyl benzamide. So this is how their acylation can be done. The next reaction is this carbylamine reaction. It's a test for all primary amines, both aliphatic and aromatic. Now any primary amine, when reacted with chloroform in presence of alcoholic KOH, gives foul smelling isocyanide along with KCl and H2O. So the formation of this isocyanide is called carbylamine reaction. Remember, even if we have aniline, this was your primary amine, this is aniline, this with chloroform and alcoholic KOH gives us foul smelling isocyanide, KCl and H2O. So that's most important, and this is a test to check the presence of primary amines. The next reaction is reaction with nitrous acid, HNO2. See, if it is primary aliphatic amine, how we get nitrous acid? By reacting it with NaNO2, HCl, 0 to 5 degrees Celsius, we call it ice cold conditions. We get, remember, alkyl diazonium salt, which is actually is unstable and undergoes hydrolysis, and it gives, you can write it like here, it gives us primary alcohol plus nitrogen plus HCl. So, even if we have, like suppose ethanamine, this on reaction with HNO2 is going to give you ethanol. Whereas the primary aromatic amines like this one, aniline, when reacted with NaNO2 HCl at 0 to 5 degrees Celsius, we call it ice cold conditions, it results in the formation of benzene, diazonium chloride called BDC. This is very stable at such a low temperature and is used to prepare a number of other compounds we'll be doing on later on. So what is most important is that the aniline gets converted into BDC, which is stable. Arene diazoniums are stable due to what? Resonance, whereas the alkyl diazonium doesn't, are not stable. They gets reduced, they gets hydrolyzed to the primary alcohols. The next reaction is reaction with benzene sulfonyl chloride, which is also called Hensberg test. And this benzene sulfonyl chloride is called Hensberg's reagent. See, it's a test to distinguish between primary, secondary and tertiary amines. Or if we are given a mixture of these three amines, with the help of this reagent we can separate them. How? Let us see this. See, if suppose we have, this is the primary amine we are having. See, suppose this is the secondary amine we are having, and this is the tertiary amine we are having. We react all these three with, let me write it in short as AR means benzene ring, with this compound which is called benzene sulfonyl chloride or Hensberg's reagent. So we will react all the three amines with this reagent. Now what we find is the primary amine, H and the Cl of this goes out, so minus HCl. So what we get in this case is this compound being formed, NHCH3. This is called N-methyl benzene sulfonamide. This also, like here, goes out, minus HCl. So we will be able to get what? N-dimethyl benzene sulfonamide. And since it doesn't have any NH bond, no reaction takes place in this case. So what we find is this is insoluble in BSC. We call it BSC, benzene sulfonyl chloride. This is soluble in BSC and this is soluble in BSC. So the test tube which we find will be insoluble in BSC will be having tertiary amine, and the two which gets dissolved in the BSC will be having primary and secondary. Or if we are given mixture of the three amines, we get a separate layer of one amine which doesn't get dissolved in BSC, and that is tertiary amine. The other two gets dissolved, that means that part will be having primary and secondary. Now we know amides are amphoteric, so we reacted them with KOH. This H goes out with this OH of this KOH, so minus water. So potassium salt is formed. it's like this, minus plus potassium. So what we find is this is soluble in KOH. If we react this secondary amines reacted product with the BSC with KOH, since it doesn't have any NH here in the amide, no reaction takes place in this case. So what we find is it is insoluble in BSC, in KOH. So the one which is insoluble in KOH is secondary, and which becomes even soluble in KOH is primary. So this is how we can easily distinguish between primary, secondary and tertiary amines, and we can separate their mixture. The next reaction is electrophilic substitution reactions. We know we have done, I have explained it to you, that the aniline group or the NH2 group when attached to benzene ring is showing plus R effect. Very strong plus R effect, so they are called, so that is why they are called strong ring activating group, and as a result they are ortho-para directing. Now let us see their first reaction, halogenation. When we take aniline and we react it with bromine, of course in bromine water, what we get is is 2,4,6 tribromo aniline. So tri-substitution takes place, tri-substitution, because NH2 group is a very strong ring activating group. If we want mono-substitution, like phenol, by changing the medium we cannot do this, because there it used to get converted into phenoxide ion, and if once we stop that, we get mono-substitution. In case of this one, we have to reduce the electron donating tendency of the NH2 group. So what we do is, we react this with anhydride in basic medium, like we take pyridine or sort of small weak bases. They gives us this acetamide. This is called acetanilide. Now this acetanilide is having system here that the carbonyl group withdraws pi electron, so N donates its electron here. So it has a resonating structure like this, in which what we find is there's a double bond between this N and this carbon. Now the nitrogen is having a positive charge and its electron donating tendency is reduced very much. That is why when this acetanilide is reacted with then bromine, of course taken in acetic acid, what we get is we get COCH3 ortho as well as para. I am drawing only the para one because that will be the major one because of the steric hindrance. We get para product, and let me remove this resonating structure also, because I think that is clear to you. Now we get this product. Now let us do its hydrolysis in basic medium, because acid will come out, and this will give us what? This NH2 Br plus acetic acid molecule. So this is how we can get mono-substitution done, by protecting the NH2 group or by the acylation of the NH2 group, and that is how we can reduce its electron donating tendency or its plus R effect, so that we can get mono product. Let us see now the nitration. See, when we do the nitration of aniline with, of course, nitric acid, we get very different result. We get ortho and para substituted products, along with which we also get meta substituted product. The most interesting is we will taking H2SO4 also, because that's a nitrating mixture. The percentage of these three products is almost as like this. It's 51%, it's 47%, and it's nearly 2%. What is most astonishing is that why we are getting meta product. Since we know that NH2 due to its plus R effect is orthopara directing. It is because in strong acidic medium, aniline gets converted into anilinium ion. Now, anilinium ion shows very strong minus I effect. As a result, it becomes meta. So, that is why we get a mixture of all these three. Now, in order to avoid this and to get para as the major one, what we have to do is we have to protect the NH2 group from getting converted into anilinium ion. How we can do that? By its acylation, the same procedure, acetic anhydride in presence of a base will convert it into acetamide or acetanilide, you can say in the other language. Now this on nitration will give us para as the major product. Now this on hydrolysis will give us para substituted para nitroaniline. Now let us see the sulfonation of aniline. See, when we react this with sulfuric acid, this being a base, this aniline, and this being an acid, they both react to form NH3 plus HSO4 minus. This is called anilinium hydrogen sulfate salt. Now, this salt at around 200 degrees Celsius, when heated, shows rearrangement and it forms NH2 SO3H. This is called para amino benzene sulfonic acid. Now this is having a basic group and an acidic group, so it shows self neutralization and it gets converted into NH3 plus SO3 minus, which is called zwitterion, the ion which contains both cationic and anionic sites. So that is how we can get zwitterion from aniline by reacting with sulfuric acid. Along with this, what you need to remember is the aromatic amines or aniline doesn't show Friedel-Crafts reactions, because being bases, Lewis bases, they react with the Lewis acids AlCl3 with FeCl3, which are taken to form what is selenium or alkyl carbocations and forms a salt. So therefore, they doesn't show Friedel-Crafts reactions. So that is how these are all the reactions we are having from amines.